So talking with you, George, gives me a vision of actually ways of teaching biochemistry that would be more interesting, easier to remember, and give a deeper understanding. Is that possible?
Well, I think so. I hope so. I mean, again, I'm an optimist. I think that if you get the right hook into a student, you can hold on to them and hold their attention, which is increasingly difficult, I find, in teaching. Attention spans are kind of a cliche. Students don't have high attention spans, blah, blah, blah. But in a way, teaching any topic, if it's done with effective storytelling, and with biochemistry, when I took it, there were no stories. There were facts, chemical structures. But as I said earlier, the stories you can tell about how, for example, a sugar like glycerol or trehalose is used in all kinds of different organisms, yeasts and flies and worms and vertebrates, frogs, Arctic beetles, to do a variety of things, prevent loss of water or compensate for the effects of losing water, increase thermal stability. So then when you go back and you say, okay, here are the pathways that are responsible for making these things, students go, oh yeah, and that's,
it makes
if you
sense.
make enough of it, yeah, it makes a lot of sense.
It's because you're adding in function to structure.
So. And I think it helps, I think retention of information is helped by it being embedded in a story.
Right.
And one of the stories, one of my favorite stories, is why sharks use this odd combination of urea and methylammonium solutes. The counteracting effects of
their
urea
cells
on
have
proteins.
these special chemicals in them.
They do, yeah. And urea destabilizes proteins. The methylammonium stabilize it, and there's no net effect when you mix them together. So that explains.
So why bother having both of them? Why not have neither of them and have this cell just do its thing without them?
Well, it's because in the marine realm, sharks have the same total concentration of solutes in their cells and blood as present in seawater. Seawater is basically sodium chloride. So the cells have to accumulate some types of solutes. They can't accumulate sodium chloride because that's too disruptive of the cell. So all osmotically concentrated animals and most bacteria build up these small organic molecules. Instead of salts, they build up small organic molecules. But these molecules have very different effects among themselves. So you have to choose a mixture, again, building up the cellular soup that gives the appropriate properties of the proteins.
So the blood or the body fluids of a shark are much more concentrated with salts and things than ours are. Is that right?
That's right, about 2 times.
Two times, because we can't live in seawater. I mean, it sucks the water right out of us.
That's right.
So in order to keep their osmolality, the concentration of salts up, they have to add something. And they manage to add 2 different things that balance each other so proteins stay about the same.
That's right.
That's so lovely. That's lovely.
Yeah, and what marine invertebrates do, crabs, shrimp, lobsters, they do something very different from what sharks do. They build up the concentrations of what are called free amino acids. These are amino acids that aren't linked into proteins, and they can build these up to concentrations of, like 4/10 molar. So again, instead of salts, they're not using the shark system, but they're using a different type of small organic molecule.
So those sound like they might be easier to adjust, the concentrations, because you synthesize them or break them down.
That's true, yeah. And one of the things that you see when you're looking at the choice of small organic molecules that organisms use to adjust their osmolality is that they're often waste products. They're things that you would have chucked out into the environment if there were no use for them. But if there's a use for them in adjusting osmolality, then these are like freebies in a way, and urea is an example of that, a protein breakdown product. And normally we excrete urea, but in some animals, they retain it to keep osmotic balance.
Thanks so much for joining us today, George.
Oh, that was fun. My pleasure. I've had a very good visit. I'm coming back. I warn you.
We're looking forward to that.
Okay, thanks very much. Thank you.
Bye-bye.